Chapter 12, rotation of a rigid body. This is a long, long chapter, and most students find it extremely challenging. So beware, you'll have to put in some extra effort. And anyway, here we go. So here's the most important thing. We're going to extend the particle model to the rigid body model. So you know how we used to say massless, frictionless pulleys? No more. So it's just going to be challenging, okay? To understand, or like here, I mean, we used to just draw the force diagram with a point. Well, if you have an extended object, you can't just draw a point. And you'll see. So it's very, very complicated. But not so bad. We'll do fine. Okay, we're going to understand the equilibrium of an extended object. Understand rotation about a fixed axis. So if I just had a bicycle wheel and I'm holding on to the axle and I just spin it, that would be rotation about a fixed axis. To understand rolling motion, so if I have the wheel and it's rolling along the floor. To introduce the vector description of rotational motion and angular momentum. So when we learned about work, we learned about the vector dot product. That was a scalar. We're going to learn a new way to multiply vectors, and we get a vector as the result. So a lot of challenging things this chapter. So we'll take it nice and easy, and you study hard, and we'll do great. Okay, so let's just review rotational kinematics, just purely review. All right, here's supposed to be a circle. Here's our angle theta in radians. Here's the radius r. Here's the arc length s. So we know that if theta is in radians, s equals r theta. You better know that. And we know r is constant, right? So r is constant because it's a circle. So if we take the derivative, the time derivative of both sides of this equation, we get ds dt equals r, which is constant, d theta dt. And what's ds dt? It's velocity, right? Because it's a meter per second, so it's a velocity. So we have velocity, and call it tangential if you really want to. You don't have to, though. Equals r. And what's this? D theta dt. So it's radians per second. That's angular velocity. That's omega. All right. So that's super important. Right? Tangential velocity equals r omega. Then let's take the time derivative of this equation. So we get dv dt. Okay, r is still constant. Pull it outside. d omega dt. Velocity over time is acceleration, so we have a sub t. R just sits there. Radians per second. What? Yeah. So this is radians per second, sorry, right? Omega is radians per second. So radians per second, that's alpha, the angular acceleration. So there you go. So I mean, you don't have to memorize these, but I would recommend you memorize this. You just use it all the time. You don't have to memorize that, but you can figure it out yourself, right? Just take the derivative. So this is crucially important, and you just get it from that, which you should know. Okay. All right, and you don't have to memorize these. You have to memorize these, right? But if you know these, this is simple. You just substitute. So the angular version of v is omega, v omega, a becomes alpha, and so forth and so on. So again, that's why I had to memorize these three, because if you know these, you can just figure these out. Okay, so there you go. So that's the kinematics for rotational problems. Okay, let's talk about some other things though. The following figures show a rotating wheel. Determine the signs plus or minus of omega and alpha. So here, it's rotating in a clockwise direction. So you just have to remember, what's the sign of omega for clockwise? It's negative. Now, it's slowing down, so what you learned a long time ago, what's true about the signs of velocity and acceleration if something is slowing down? They're opposite. So if this is plus, this has to, if this is minus, that has to be plus. Okay. Now here something is rotating counterclockwise. And remember, that was defined to be positive omega. So positive omega. But it's also slowing down, so these have to be opposite signs, so alpha has to be negative. Okay, so that's just all review. You better know that. All right. Okay. Now, like I said a couple of minutes ago, we're going to extend the particle model to the rigid body model. So if I throw this, will you be able to see it? Okay. All right. Okay. So let's throw this thing, and I'm going to purposely put a spin on it. Okay. Now let me back up. If I throw a tennis ball, which I'm assuming is a particle, it undergoes perfect parabolic motion, right? But if I do it to this, okay, let's see if I can do it. Okay. Now, do you think that every particle making up this meter stick undergoes perfect parabolic motion? Of course not. No way. I mean, it's like, pick up the end of the meter stick. I mean, it was spinning. I mean, it's completely complicated, right? However, there's one point on this meter stick that actually did undergo perfect parabolic motion. And that spot or location on the meter stick is called the meter stick center of mass. Now, meter stick's pretty simple to figure out. You just balance, right? So it's going to be at the halfway point. So basically, what we're saying is there's something called the center of mass. The center of mass undergoes perfect parabolic motion, just like a particle. Also, you can consider all of the mass of the meter stick to be located at that center of mass, and then just use the kinematic equations. So that's not so bad. Okay. So here, oh, not yet. What are you showing that for? Sorry. Oh, I forgot to show you this. Sorry. Oh, brother. Sorry. Back up. That's okay. So I don't think I've ever talked about the sign, the direction of omega. Maybe I have. I don't remember. So, but you need to know it, especially for this chapter. So let's say we have a disk rotating as shown. So we have a disk, right? Like a turntable or something like that. And what is the direction of omega? Now, we've just talked about clockwise and counterclockwise, but that's all good and everything. But omega is a vector, And so you have to use something called the right-hand rule to figure out the vector direction of omega, the vector direction. We've just figured out magnitude, like if velocity positive, velocity negative, right? Velocity positive, velocity negative. That's all we've really done. But now we've got to kind of go to a new level, okay? So this is how you figure out the direction of the vector omega. So here's your turntable. It's going, let's say it's going counterclockwise according to me. So this is called the rotation axis. So what you do, right hand, sorry lefties, right hand, you grab the rotation axis with your right hand. Your fingers are in the direction of motion. So my fingers are pointing counterclockwise. Stick up your thumb. Your thumb is in the direction of vector omega. Weird, right? But it works. Okay? So look. So you have to imagine, so you have the spinning disk. So you have to just imagine the rotation axis. So just imagine, you're just grabbing a meter stick or a rod or something like that. Okay, using your right hand, curl your fingers in the direction of rotation. Like I said, counterclockwise for me, right? with your thumb along the rotation axis. Your thumb is then pointing in the direction of vector omega. So that's called the right-hand rule. We're going to have a lot of right-hand rules later on in this chapter. And if you take Physics 220, oh my gosh, all sorts of right-hand rules. Okay, let's say we have the disk is spinning clockwise according to me. Here's the rotation axis. I have to grab it like this now because my fingers are pointing clockwise. And where's my thumb point? Down. So vector omega would point down. Okay, remember that. We're going to use it. Okay, let's get back to this. All right, so here's a hammer. I mean, obviously a hammer is a non-uniform object, right? So if you take a hammer and you just throw it however you want to, again, there's this one point in the hammer, the balance point, or the center of mass. And look what it does. It undergoes perfect parabolic motion, right? So we can just assume that all of the mass is concentrated at that center of mass. Okay, that's all there is to it. Okay. All right, so here. So this is a baseball bat made out of wood, like it used to do a long time ago. So where do you think is the approximate center of mass? So pause your video, and it's solid, by the way, right? Solid wood. So pause your video and figure it out. Okay, another it's a balance point, right? I mean, that's not going to balance there. It's not going to balance there. It's not going to balance there either because there's so much more weight over here. It's probably somewhere around here is the balance point. So the center of mass is at that balance point, which is somewhere around D. Again, you know, the balance point of a meter stick, if it's a uniform meter stick, it's pretty simple, right? Just right in the middle. Here, where's the center of mass of a donut? Well, it's actually here. So I like to show this photograph because it shows that the center of mass doesn't actually have to be in the object. It could be outside the object, right? So the center of mass of a donut's not even touching the donut. Okay? Center. All right, now we got to learn how to calculate the center of mass. Okay, so first we'll start easy. So we're going to just say we have particles. Okay, particles. So every particle has like particle 1 has mass m1, particle 2 has mass m2, and so forth. Okay. So this is the formula to calculate the center of mass relative to an origin. You can't just say, what's the center of mass? I mean, I guess you could for a donut or something like that, but something like this, when you just have one dimension, you got to say, I want the center of mass relative to a particular point. Okay? So we're calculating the center of mass relative to this origin, right? And you can see that x1 is the distance from the origin to the center of m1, to the center of mass of m1. x2 is the distance from the origin to the center of mass of m2. Okay? All right. Okay? So let's do it. All right. So that's the formula. So you just take m1 multiplied by x1, take m2 multiplied by x2, and m3 times x, and you just add all these products, and then you divide by the total mass. So you can write, this is too much trouble to write it like that, right? So just write it in a nice compact way. It's 1 divided by the total mass, uppercase M, total mass. Then you have this sum, m1, x1 plus m2, x2 plus m3, x3, da, 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 da. Okay? Now, just look at the picture here, you know. So if this mass is about the same as this mass, which kind of looks like, right? The center mass is smack dab in the middle. Kind of makes sense, right? On the other hand, if this guy is way more massive than this guy, where do you think the center, where's the balance point going to be? It's going to be somewhere over here. Okay? All right. So that should make sense, I hope. Okay, so the moon orbits Earth. No kidding. They are separated by a center-to-center distance of whatever. Earth's mass is blah, blah, and that of the moon is blah, blah. A, how far does the center of mass lie from Earth's center? What is your answer as a percentage of the center-to-center distance? Okay? So what you want to do is you want to figure out the center of mass relative to Earth's center. So Earth's center is the origin. So use this formula. So you do this, all right? So use this formula and say that the center of the Earth is the origin, and find the center of mass for the Earth-Moon system. So please pause your video and do A as well as B. So pause your video and figure it out. All right, let's do it. I assume you've done it, but let's check if you did it right. So X center of mass. Well, what's the formula? Let's just copy the formula. So mass Earth, X Earth, plus mass Moon, X Moon, over mass Earth, plus mass Moon. Right? That's just the formula. Okay. Now, remember, the X is the distance from the origin to the center of mass of the object. Okay? So what is X Earth? I mean, the origin is the center of the Earth. So what's the distance from the center of the Earth to the center of the Earth? 0, right? So all I'm saying is that this X Earth is 0, right? Because we had the center of the Earth being the origin. So goodbye there. That's nice. Makes it a little bit nicer, you know. So now what I have to do is the mass of the moon. Where did that go? 7.35 times 10 to the 22 kilogram. And what's X Moon? So X Moon is the distance between Earth center and Moon center. So right there, 3.85 times 10 to the 8th. And then the total mass is the total mass. So you do that, and you get 4.67 times 10 to the 6th meters. All right? So that's where the center of mass is, okay? It's 4.67 times, so basically 4.67 million meters away from the center of the Earth. Now that sounds like a lot, right? I mean, wow, 6 million meters, you know? Or, sorry, almost 5 million meters. But now let's do, what is the answer as a percentage of the center-to-center distance? So let's see that. So 4.67 times 10 to the 6 meters. But what's the center-to-center distance? 3.85 times 10 to the 8th meters, right? Then it said percent. Let's multiply it by 100%. Okay? So it's 1%. All right? So it's nothing. So I mean, the center of mass of the Moon-Earth system is very, very close to the center of the Earth. Okay, when you look at, you know, how far the Moon is from the Earth. Okay, kind of makes sense, right? Because I mean, look at what's the mass of the Moon compared to the mass of the Earth? Not much, you know. I mean, it's 100th as much, which is like a percent. Okay. So here's a nice simulation that you should play with. It's a binary star. That means there's 2 stars and they orbit each other. And you can play around with the different masses and see where the center of mass is located. So like if they're both, you know, equal mass, then the center of mass is going to be in the middle, right? If one of them is giant compared to the other one, the center of mass is going to be closer to the more massive star. So just play around with it. It's kind of fun. Okay. Golly, this formula is only for 1 dimension. Well, what if you have 2? Well, not a big deal, right? It's the same formula. You just have an X with X's and you have a Y with Y's. So it's the same formula. You just have Y's rather than X. Not a big deal, right? Okay, but we got to get practice. So here you go. So here's a 100-gram mass, 300-gram mass, 200-gram mass. You want to find the center of mass relative to this point. Okay? So before you do your work, just think about it for a minute. So we want to get the x center of mass. Then we want to get the y center of mass. Now think about it. Along the x, here's 100. What do we have here? 500, right? Just looking at the x. And so you have to admit the center of mass is going to be over here somewhere, right? Now look at the y. Here we have 400. Here we have 200. So where's the y center mass going to be? Down here somewhere, right? Okay, so this is the origin. So pause your video and figure it out, please. By the way, this is the easiest part of the chapter. Okay, let's do it. I hope you've done it. So x center of mass. All right, I'm just going to write out the formula, whatever. So MA XA plus MB XB plus MC over XC divided by the total mass. Okay, that's what it is. All right, now let's remember, this is the origin. So what's XA? 0. That's nice. So this goes away. All right, so I just have MB, so by the way, we don't have to convert it to kilograms because we can have grams up here and grams here, so it cancels, right? So you don't have to, if you have masses on the top and on the bottom, numerator, denominator, just use the same units and you'll be fine. So 200 grams. Okay, what's XB? 10 centimeters. Plus MC, 300 grams. And what's X for C? 10 centimeters. All right. And then the bottom we have, let's just be lazy, come on. 100, 200 is 300 plus 300, 600. 600 grams, right? 600 grams. So I promise you do that, you get 8.33. 8.33 centimeters. Might just leave it in centimeters, right? I mean, the problem is centimeters, okay? Okay, does that make sense? Of course it makes sense. We knew the center mass was going to be closer to this because you get all this mass, you know, at x equals 10, right? So 8.33, that makes sense. Good, makes sense. Let's do the y. Let's just write the formula. MAYA plus MBYB plus MCYC all over the masses, the sum. Okay, once again, what's YA? 0, right? Because this is the origin. So goodbye that. All right, so 200 grams. Wait a second, what's Y? Oh yeah, hold on. What's YC? Let's hold our horses here. All right, what's YC? YC is also 0, agree? Because this is the Y equals 0, so that's 0. That's great. So goodbye that, huh? So all we have is 200 grams times YB, which is 10 centimeters, all over the total. Right? The total is still 600. Okay, and that's 3.33 centimeters. Right? So the Y center of mass is like here, right? Does that make sense? Of course it makes sense, because here you have 400 grams at Y equals 0, you have 200 grams at Y equals 10, so you know it's going to be down here somewhere. So there you go. Makes sense. All right, here's a challenging question. Some people get it right away. Some people have a really hard time with it. But it's okay. Just don't worry about it. Just do your best. A 1 kilogram rock is supported by a massless string. So we don't care about the string, you know. I mean, we know it has to hold a rock, but that's all. Okay, from one end of a meter stick. What is the mass of the meter stick if it's balanced by a support force at the 0.25 meter mark? Hint, think about the center of mass of the meter stick. So I was going to give you a hint, but I decided not to. So you pause your video and figure it out. And don't quit. Figure it out. This is a good one. Okay, I hope you figured it out. Okay, so where's the center of mass of the meter stick? At the center, right here. So basically what you're thinking of, or what you're visualizing, you have a kilogram here, and all you're seeing, again, you're saying that the entire mass of the meter stick is here, right? If you want to put it by a string, it doesn't really matter, but the entire mass of the meter stick is right here. So here you have a kilogram located at 0.25 away from the balance. Here you have an unknown mass located at 0.25 from the balance. What does this mass have to be? It has to be that mass, right? If it's balanced, so it's 1 kilogram. Okay? We'll do that a different way later on, but that's all right. All right, let's see. Now, all these formulas that we've seen so far, you know, those are with points, right? But we don't want points. We want rigid bodies. I mean, that's where we're going. So, you ready? All right, so for rigid bodies, okay, what's a rigid body, like a meter stick? You know, what's a meter stick? It's made out of a gazillion molecules, right? Or you can say that the meter stick is made out of a gazillion point particles, right? That's kind of where we're going, right? So here is these are the formulas for the center of masses for a rigid body. So what in the world is okay, so the dm, we're saying that the dm is the mass of each little individual molecule or atom or whatever you want to call it, making up the meter stick, okay? So we're assuming that every molecule has the same mass, which is okay. And x is just the distance from the origin to each individual mass, to each dm. All right? So again, you know, you learned this in calculus, right? What's a sum? A sum is an integral, right? Or maybe I should have said, what's an integral? It's a sum, right? Yeah. All right, so integral is just a sum. So here you still have your 1 over m. Here you have this is the x, right? And the x is, and the mass is the dm. So it's the same thing, you know? It's just an integral is an infinite sum, right? That's all. So these are the equations for the center of mass. Now, this should freak you out a little bit. When you're in calculus, you know, you do things like this, right? X squared dx, or, I don't know, cosine 2 pi t dt, or something like that, right? But have you ever done an integral, you know, x dm? What in the world is a dm? I mean, how do you do that? Okay, so we have to learn how to do integrals like this. And I should warn you, we're going to be doing this later on in this chapter. It's not just now, we're going to be doing it later on in this chapter. We'll also be doing it in Physics 220, which if you're going to go to medical school, you better take it. If you just want to go computer science, you better take it. It's a good class. All right, so all I'm saying is it's incredibly important to learn how to do these integrals. Okay? All right, so let's do it. So, I mean, what do we want? I mean, there's no way you can do this. We have to somehow change it so we have an integral, some function of x times a dx, right? Or maybe, you know, if it's like a y dm, we want that to be integral function of y times dy. So what I'm saying is we got to substitute for the dm because we have to have something like that or like that in order to integrate. So that's what we're going to learn how to do. how do we substitute? Get rid of the dm. That's really what we want to do. Get rid of dm. All right? Okay, here we go. Okay, so let's assume we have a one-dimensional object with mass m, length L. What's a one-dimensional object? Just think of like a thread. You know, it's so narrow, all you really care about is the length. Okay? It's an approximation, I know, but it's okay. All right? So one-dimensional object, all it has is mass and length. We don't talk about the diameter because it's so small. We don't worry about it. Okay, so here's the thing. The thing that saves us, that allows us to do this, is we're going to say the object has uniform density. What's that mean? It just means that the density is the same, right? The density is the same throughout. Okay? Density is the same throughout. All right, so here we go. So what's the density? We're talking about mass density. So mass density is, mass. Okay, in chemistry, you learn that density is mass over volume, right? But here, we have a one-dimensional object, so volume is kind of foolish to talk about. The only thing you have is length, right? Length. So we're going to have mass over length, right? And it's constant. That's what it means to be uniform. Constant, Uniform density, constant. Okay, so what's the density of this thing? The density, which is uniform, is equal to the total mass over the total length. No kidding. All right, that's cool. But now let's say we want to look at just a little tiny piece of this object. So we're going to say that a piece, let's say it's a molecule or something, I don't know, whatever. Just a piece of this object. So we're going to say that the mass of this little tiny piece is dm, and the length of this tiny little thing is dx. All right? Well, if it's uniform density, that means this density is equal to the little mass over the little length, right? I mean, that's what it means to be uniform, right? We could say that half the mass over half the length equals 3/4 the mass over 3/4 the length, whatever. It's uniform. So the total mass over the total length equals a tiny little mass of that thing divided by the little length of that thing. So you say, whoopee, who cares? Well, watch. Solve for dm. So dm, therefore, equals total mass over total length times dx. Now you should be saying, oh, awesome, right? Right? I mean, that's cool, because now we have our dx. That's what we want. Now we have our dx. So, we used to have this, right? X center mass equals 1 over m integral x dm. Correct? That's what we had. Well, now, what do we have? We have 1 over m. This is the big M, the total mass, right? And then we have x, but what's our dm? Our dm now is total mass over total length times dx. Well, masses kill, L comes out. We get 1 over L integral x dx. Yay! All right? So we can do it, right? We can do it. So all I'm saying is you have to do this substitution in order to actually be able to evaluate the integral, right? Okay, now that's a one-dimensional object. Let's do a two-dimensional object. It's a bit trickier because you have an x and a y now, right? With a one-dimensional, you just have an x. With a two, you have an x and a y. Okay, so now, what's the total density? Well, now you have again, what's a two-dimensional object? A piece of saran wrap, right? We're ignoring the thickness, but we're saying it has an area, all right? So the density is just the mass over the area. Okay, now now we're going to make a slice, right? So here's a slice. So we're saying that the slice has mass dm and area dA. So if the density is uniform, which it is, the total mass over the total area equals the little mass over the little area. All right? I mean, that's all there is to it. So therefore, dm equals m over a dA. Okay, now hold it. What is dA? I mean, what is it? Well, it depends what you're doing. So okay. So here, okay. So let's say we have our slice this way. So what is the area of this little slice? Well, thickness dx times y, right? This is y, this is dx. So dA is y dx. All right, so that's cool, you know, because, okay, let's do that. So we'll have dm equals m over a, dA is y dx, okay? So that will mean so what is this going to be? So this will allow us to do the x, right? The x center mass, because we have a dx, okay? But let's say we want to get the dy. I mean the the y center of mass, all right? So this is for x center of mass because we have a dx. So we took a slice like this. But now let's say we want to do y center of mass. Now we've got to get a slice like this because, you know, if we have a y center of mass, we've got to get a dy, right? I mean, we have this y right here. If you have a y right here, we want to get a dy, you know? So let's do that. Okay, so here, what is the area of this slice? Well, now it's the total x times the little dy, right? So here, the dA is the length x times the width dy. All right? That's all there is. So in other words, we'd have y center mass equals 1 over m integral y dm, but dm is m over a dA, and dA is x dy. Right, so okay, and again, y is going to be some function of x, you know, sorry, x is going to be a function of y, right? So you're just going to have y's here with a dy. Oh boy, I hope that made sense. Okay, so all I'm saying is that's easy. This is more challenging, right? dm equals mass over a times dA, but then you got to figure out what dA is. If you want to get an x center of mass, you're going to make your slice like this, so you have a dx. If you want to get a y center of mass, you're going to make your slice like this, so you have a dy. And that's all there is to it. I mean, it's not so bad. Okay, so next time, we're going to calculate the center of mass of this. So I'm going to do the x, and I'll have you do the y. And if you do, well, and that's how you learn how to do it. And again, we're going to be doing something similar to this later on in this chapter, and we'll do things like this in Physics 220. So it's an essential skill to obtain. Thank you.